Hey guys, well, I finally managed to get outside a couple of days ago. We had a rare combination of clear skies and a Saturday and a day where I didn't have to do anything intelligent. So I managed to get the previous scope out, the SCT out, and wanted to try out the Celestron off-axis guider along with the new camera. So this is the first time I've put these pieces together and done anything. And I wanted to share with you a little bit some of the lessons I learned in the process. So here's the imaging setup. I've got the focal reducer installed. It's an f6.3 for my C9.25 Smith Cassegrain. I've got, of course, the Celestron off-axis guider. You can't see the guide camera because it's rotated around and hidden behind the off-axis guider body, but I'll show you that in a minute. And, of course, I've got the filter wheel and the ASI 1600. And importantly, I don't have the guide scope. And this it changes the weights and balance significantly. For one thing, in balancing in deck, I had to slide the scope a good bit forward. I was actually worried that I was going to run out of room back here in the back, but it all balanced perfectly. And on the good news side, I got to move the counterweights up off the bottom of the bar and move them up quite a bit. So it's a significant reduction in the mass moment of inertia, which should help guiding just in and of itself. So that's what the system setup looked like. Now, during the night, I spent time just trying to get this camera in focus. I was able to do that with some effort. I also was trying to find a guide star, and this was very difficult. Apparently I didn't have some settings set right with the guide camera. You should go with full gain and maybe a 1 second exposure, but I rotated that guide camera around and never saw a guide star. And before too long, my laptop battery and my patience ran down, so I had to go inside. And I went inside not ever having seen a guide star in the field of view around this target, which was M101. This is the orientation I ended up with. I've since brought the scope back in, and you can see the main camera here. The writing on the bottom of the ASI 160 is on the bottom of the ASI 160 sensor, and this line is parallel with the long direction of the sensor. So if you measure that angle out, it comes out to about 104 degrees. Meanwhile, my guide camera is about 88 degrees relative to the sensor axis. So these are the numbers I ended up with. As I said, I didn't see any guide stars, so I did actually have them in view. I just didn't have the camera in the right settings to show them to me. But let's take these numbers and go over to Stellarium. So that 104 degree angle is the one that I would enter here in the Sensors tab under the ASI 1600. I've got obviously the sensor size located here, the pixel size, and I put in this minus 104 degrees, which corresponds to that angle that I showed you in the PowerPoint slide. Now, for the off-axis guider, I put in the 88. So based on these two numbers, I can then see what I should have been seeing in the field of view. Now, for the M101, notice that this up here, this little guy up here, is NGC 5477. So I didn't plan this, but the guide camera just happened to be oriented where it could see several stars. In theory, there's a good 5 or 6 stars there. If I had left it up here or down here, I might have been I wouldn't have been surprised because I didn't see these stars when I was outside. Now let's go over to PixInsight to see how the image that I took corresponds to what we're seeing here in this Stellarium view. Okay, so here's one sub that I took with the luminance filter. It's 100 seconds long, a gain of 1. There's not much to see here. There's a couple of things. There's the very faint core of M101. I can make out the hint of the spiral arms. You may not be able to on the video. But another thing that jumps out at you is this dark band over here. Now, it's not black over here. Stars are shining through, so it's just a band of shadow, if you will, that's on this side of the image. Now, if we go to the script, image analysis, image solver, we'll come up with these results. And this is kind of interesting. Here's that 104 degrees that we measured. All right, so we're confirming that. It's 104.8 degrees. The other thing that's interesting, is important to note, is that this script identifies the effective focal length of your imaging train, and in this case it's telling me that it's 1314 millimeters. Well, if you calculate out the theoretical number, starting with the focal length, or the aperture of 235 millimeters multiplied by the focal number of the reducer, 6.3, you'll come up with 1480 as the effective focal length, or as the theoretical focal length. So this is a good bit less. This is the number that you should take and enter into PhD2 for the guide camera, or the guide scope focal length, not the theoretical number. I think you might get better guiding results if you have the accurate focal length. So that's what I did with this number. I entered this into PhD2 for the guiding, using the off-axis guider. So that's some useful information coming from there. The second thing you can do with the script is do the render and then annotate image, and then that's where I come up with, and you'll see right up here at the top of the image, NGC 5477. Well, that's exactly what we're seeing in Stellarium. So there's NGC 5477, just exactly where we expect it, which is good confirmation that what we should be seeing over here should be these guide stars. Now let's go back to PixInsight and look at the image from the guiding sensor. So I use SharpCap to take a one-shot image from the guide camera, and you can see here's this arc of those 3 stars. There's actually more stars here, and the star on the other side. You'll notice that this image is flipped. It's mirrored about this long axis of the sensor. This direction corresponds to the direction that light travels down the tube, and then it reflects off the prism, and that's what causes this mirror flip of this image. So we see the 3 stars going this way and the opposing star over here, whereas in Stellarium we see the 3 stars up here and then the other star over here. But what we're not seeing is this star. So let's go back and take a look at what's going on with why we're not seeing this star. You can see in this image, this is corresponds to the light hitting the bottom of the prism. This is the top of the prism. Things get very dark. This is not like the shadow zone of this part of the imaging sensor. This is absolute darkness. I've stretched this image and there simply are no stars in that field of view up there. So we're not seeing anything up here for the roughly a good 25% to 30% of the sensor. Now, in order to understand why we're not seeing that, let's go back to the CAD program where we have this drawn up. So here you see the imaging train. I've got the SCT drawn. This is the secondary mirror. I'm not showing the spherical primary mirror here. But you can see here's the camera, here's the filter wheel, the off-axis guider, body, guide camera, the focal reducer, and then the body of the telescope here. Now, what I've drawn several lines here. There's an opening in the SCT that's about 44.5 millimeters in diameter. And that tube runs up, and I'm sure it's part of the support system for the spherical mirror that it rides along as you focus move the mirror while focusing. But that tube is the limiting feature that prevents light from, that can block light. And so I've drawn these 2 outer lines represent the path of light the maximum extent of the light that can get through that tube. And you'll notice if we zoom in just a little bit here, that outer edge is clipping the prism. So any light that comes in above this, that's out of this field of view, above here, is not getting to the prism, and therefore it's not getting to this back edge or the top edge of the sensor, the guiding sensor. On the other hand, I can see anything coming from the bottom of the prism up to that point. And so this is explaining why we can't see, or why we have a black zone at the top end of that imaging sensor. Now you could say, well, let's just lower the prism so that we can see that light. The problem with that is this line represents the outer edge of the light reaching my imaging sensor in its longest orientation. So I'm just barely missing, I'm just on the verge of blocking light to the imaging sensor, which I definitely don't want to do. We are getting a shadowing effect. It's not blocking the light. We can see the stars, but there is a shadowing effect there. So the prism is about as far down as I can go without actually blocking the imaging sensor. So it has to be about right here, which means I'm not going to be able to make use of this portion of the sensor, the guide sensor. So knowing that I can't make use of the top edge of this sensor, we need to go in and adjust the parameters for the off-axis guider so that it accurately reflects what I'm actually seeing in the scope. So if I go back to the properties here, I can't use this full 11.3 millimeters here. I'm going to change that to about 8.5. It's just a guess for how much of the sensor that I can actually make use of. And now when I close that down, you can see our imaging, or our donut, has reduced in size, and now this star that I was able to see, if I could make full use of the prism, is now outside of my field of view. Still, there are plenty of stars here, but this gets to be a little bit more dicey when we start going to take out the focal reducer and go to the full focal length of the system. Now I've reduced that outer edge of the my ability to see these stars, potential guide stars, out here. And that's just the price of doing business, I suppose. Now, one of the things that I did, just because I was running out of things to do and guiding wasn't that great, it was kind of gusty, so I was not getting great guiding results, at least not consistently. I decided to swing over to the bubble nebula and just I typed in these values, so I had this orientation, so I knew where my imaging sensor, how my imaging sensor was oriented, and I knew how my guide camera and off-axis guider were oriented. So I just swung over to a target that just happened to be up and just wanted to see what it looked like, and that was the bubble nebula. And so here's the bubble nebula. You'll see that there are a couple of stars here that I should be able to see given my orientation. So now let's go back over to PixInsight to see what I saw when I took a couple of pictures over here. Guide camera was seeing this image, so there are plenty of stars there, not just the ones that I'm seeing that Stellarium is showing me, but there are plenty of stars to use for guide stars, some very good ones. Here's a picture that I took, and this is in an HA image at 200 seconds, and it's actually very good. It actually comes out a lot of good data for one exposure, and I'm looking forward to coming back to this target and actually trying to image it. I think we'll get a pretty decent image out of it, although I probably will take out the focal reducer and see if I can just get a zoomed in picture of the bubble itself. And let's go back to Stellarium to see what that would look like. So if I take out the focal reducer, I'll come over here, and now there's no focal reducer, so I'm zoomed in. It looks like there'll be plenty of guide stars around to play with, so that's good. There shouldn't be any trouble using the off-axis guider with this particular target. Let's swing back over to M101. And the fundamental question we have is, okay, so let's say that I'm going to decide to take a picture of M101 and I want to set up my off-axis guider ahead of time so that I don't have to go out fishing around in the dark for guide stars. Now, which star can I pick? Well, you want to pick a bright one, and you want to pick one that won't be presumably too near the bottom or top of the imaging sensor itself. So you might check this one. This star here is magnitude 9. This is a magnitude 8.8. This is a good one, and it's a magnitude 8.1. So of all the stars that'll be in this donut of visibility, this one looks like the best guide star. Now, if I'm going to set up my guiding system, my off-axis guider and my imaging system, before I go outside, and to avoid not having to search for a guide star, what can I do with this picture here that allows me to orient things properly? Well, first of all, the thing I'm going to do, I'm going to go back to the settings and change this to a 90, the orientation of my camera, which means the long axis, the long side of the imaging sensor is parallel to the ground in the home position. When the counterweights are down, scope is up, the long axis of the imaging sensor is parallel to the ground when I type in 90 here. And I'm going to type in 0 for the guide camera orientation. Now when I do that, now I've got the 90 degrees, I've got the 0 degrees for the off-axis guider. You can see the off-axis guider is directly above the sensor here. I'm going to use a screen capture utility. I'm going to use the snipping tool to grab a picture of this portion of the sky here. And then I'm going to go back over to PowerPoint and I'll paste that in. Now, there's a couple of things we need to do here. First of all, we need to orient this thing in a manner so that we're seeing what the guide camera would be seeing. So we need to take this image and flip it vertical and then flip it horizontal. All right. Now, the next thing we need to do is align this so that it's consistent with how the guide camera would be oriented if we've got the scope inside sitting on a table and we're setting things up before we go out and put it on the mount, which is my normal way of operating. I need to make this line, this long line of the imaging sensor, parallel to the ground. So I'm going to draw a reference line on here, horizontal. I'm going to color it yellow just so we can see it and maybe build it up a little bit in terms of its length or width. And just for grins, I'm going to line it up with the center of the image and extend this out there. All right, so now I'm going to move this up and we'll zoom in on this. Now what I want to do is take this edge of the sensor and rotate it so it's horizontal. So I'm going to highlight the picture. I'm going to go over to Format, Size, and put my cursor in the rotation and then start pressing the up and down arrows until it moves in the right direction. That was the wrong direction. So now I'm just pressing the down arrow. And I'm just going to stop when I get it to where it's basically parallel, which it is right there. Now that's a minus 22 degree rotation. That's irrelevant. We're just trying to get this thing set up. And as you can see, if I move that line up, boom, there it is going right through, right parallel to the edge of the sensor. Now what I want to do, this is our target star. This is the one we want to center our off-axis guider on for that night's imaging. So now I'm going to highlight the line and I'm going to rotate it so that the line goes through that star from the center of our image up through the center of the star. Once again, I'll put my cursor in the rotation box and I'll just rotate that line. Notice how the line is still passing through the center of the image here. And when I get up to there, it looks like I've got an angle of 34 degrees. So that means I need to rotate the guide camera, the off-axis guider, and the guide camera over here until I have 34 degrees between this line to the star and the horizontal. Now, how do we implement that? Well, in this case, as you set your scope up and it's sitting on the table, you would have the although the location of the imaging sensor doesn't matter at this stage, the guide camera would be vertical, and now you want to rotate it so that it's in the right orientation to match that 34 degrees that we were looking at off the horizontal. I've got an app on my cell phone, my smartphone, called the Inclinometer app. It's for Android, but I'm sure there's something equivalent for the iPhone. And this is a screenshot from the smartphone as I was holding it up against this guide camera here. So what you would do is just rotate the guide camera around, checking so often with your Inclinometer app to see what this angle is, and I would rotate this. Now in this case it would be rotated over here. The guide camera would be over here and it would be 34 degrees off the horizontal. So I would wait till this read positive 34 with it being over here. And so once I lock that down in that position, now I'm pretty confident that that guide star that I was looking for will be in the center of the field of view of this sensor. And then I can very carefully orient this imaging sensor however I want it for framing purposes. But I need to go back when I've messed around with all those thumb screws. I need to go back around and make sure that the guide camera is 34 degrees off the horizontal. So just summarizing some of the observations from this first night out and first trial of the Celestron off-axis guider. First of all, removing the guide scope is awesome. It's great to get rid of all that mass hanging up there, and it's very easy to achieve RA balance now with that big mass removed. This should improve the responsiveness to the RA guidance commands because of the reduction in inertia. And I did see some evidence of the improved guiding, but there were a lot of wind gusts that interfered with guiding overall. So the jury's still out as to how much improvement I'm actually going to get with this setup using the off-axis guider. I'm really impressed with the ASI 174 Mini. It sees stars that Stellarium doesn't show me, which is good. I do highly recommend that if you're using this in an off-axis guider application, set the gain to a maximum and an exposure of 1 second. You don't want to get too large of an exposure because, after all, that exposure is what you're going to be using in PhD2. And I tend to run around the 1 second to 2 second range. I need more updates for my mount than some people need for theirs. Typically, I guess most people might use a 2 to 3 second update rate. But if you can see stars with 1 second of exposure, then you're in pretty good. You're a pretty good setup, and you're ready to do some guiding. But it's a very sensitive camera, and I'm really impressed with it for its use in the off-axis guider. The off-axis guider has a large prism, which is a very good thing, and it pairs nicely with the large sensor of the ASI 174. However, the design of the scope, of my particular scope, prevents all of that light from getting to the guide sensor. It gets blocked by that interior tube, and so I only see roughly 75% of the area of the guide camera. So that's just one thing you got to live with, I guess. I found that blindly searching for guide stars at night is a beating. So I highly recommend that you plan ahead. And Stellarium is a great tool, and I'm sure there are other tools. I'm just using Stellarium. But yeah, using Stellarium in a smartphone, you can probably identify your guide star and center it in the field of view of your guide camera before you even go outside, and I highly recommend that. I use a plate solver, and in this case I was using the image analysis scripts within PixInsight to identify the true focal length of the imaging train, and then that's the number that I put into PhD2 for guiding. That way I think we get better calibration results, more accurate calibration results. So I would recommend you do that as well. I need more imaging time with this system in order to, I guess, properly gauge what kind of an improvement that I'm getting with guiding by eliminating the excessive mass, and also using an imaging scale in the guide camera that is much finer than what I had been using with that 600 millimeter focal length guide scope that I was using. So there are a couple of benefits here. One of the downsides, obviously, of the off-axis guider is finding guide stars, and some targets will be very challenging, but hopefully you can plan ahead. Well, I hope this stuff helps you, and good luck.